Hey folks, welcome back to the Curlyboi Theatre. We are in our last block of talks for the day. I can't believe we've made it this far. It's been a good one. And next up, we have Nick Moore, who's going to be talking about decoding programming beyond text files. I'm very excited to hear this talk. Nick is a freelance software consultant from Melbourne, Australia. Nick is also online. His connection's just not up to video streaming at the moment, but he will be lurking in the Venulous chat so that he will be able to heckle himself and answer all of your questions for you. He would also like me to tell you that the URL on the first slide has a transcript of this talk if anybody wants that for later. But other than that, I will take myself off and let Nick start.
We're used to thinking of programs as text files. According to computing folklore, the first step on the road to being a real programmer is to pick a text editor that reflects your personal style. We choose our favourite text editor, we argue passionately about code formatting standards, and we feel guilty when our diffs are ugly. But what if these things are just a vestigial hangover from computing's earliest evolution? As Gerald Weinberg says, things are like they are because they got that way. Complex systems don't just happen, they evolve through a series of decisions, each of which seemed like a good idea at the time. A lot of the things we take for granted in programming come from these early decisions. It's easy to assume that they're purposeful, even immutable. In this talk, I'll discuss some alternatives and where they could perhaps lead. But first, some computing history. This story begins in the mid-19th century, when the first printing telegraphs transformed telegraphy from using Morse code to using a typewriter-like keyboard and a mechanical printer. Using Morse code required an operator to tap out a difficult encoding of dots and dashes and to receive messages by translating these audible signals back into letters. By switching to an automatic encoder, messages could be sent with less training, and having messages print on paper allowed records to be kept. Over the next 100 years or so, this technology developed into the teleprinter, a device which allowed an operator to type a message on a standard typewriter keyboard and have it printed instantly on the other side of the world. Various standards evolved to encode characters, but eventually most devices settled on ASCII as a data interchange format. ASCII defines 7-bit characters with 32 control characters used to do things like advance the printer paper or ring a bell. If you've ever wondered why your Linux terminal thinks it's a typewriter, or why it misbehaves when you cat a binary, this is why. During the same period, punch cards were also being developed as a storage medium. Punch cards were used for machine control, music, and information storage. A whole industry sprang up to support the use of cards for indexing and collation. Methods for sorting and searching notched cards using long needles were invented. Very early computers were developed to process cards by counting and accumulating values punched into them. The information age had begun. There were many standards developed for machine-readable punched cards, with different dimensions and numbers of holes. But the IBM 80-column card, introduced in 1928, became the most common standard for punched cards. Millions of these cards were produced. The 80-column IBM card led naturally to the 80-column IBM video terminal. Each terminal row could display the contents of a single punched card. Early languages like Fortran began in this era. They are very line-oriented. Each statement is a single line suitable for punching into a single card. Punch cards themselves can't easily be edited, but programs can be corrected and rearranged a line at a time by inserting, removing, and replacing cards from the deck. Sections of code can be gathered into modules, held with rubber bands, and these modules can be copied, shared between programs, and stored on shelves. Literal libraries of code. To write a program, the programmer punches statements into cards, one statement per card. When the program is ready to be run, the cards are fed to another program, the compiler. This compiles them into a long strip of punch tape. Punch tape is very much denser than punched cards, with binary representation and no extraneous whitespace, but it is much harder for humans to read and manipulate. And this split between the continuous and the line-oriented has continued to this day, with files divided into easily manipulated, line-oriented text files, like decks of punched cards, and compact but difficult to edit binary files, like punch tapes. While punched cards often had their contents typed along the top edge, actually reading code in this way was not very convenient, so people tended to print out their programs for analysis. Pictured here is MIT computer scientist Margaret Hamilton with the listings of the Apollo mission lunar module software developed by her and her team. There's a lot of code there. Printing code continued on into the 90s. When I first started my computer science degree, most of us accessed the shared Unix computers through 80-column VT220 terminals, and it was pretty normal to print your code out on the enormous dot matrix printers so you could read it while debugging your code on the limited space of the 80 by 25 monitor. With larger monitors, printing code is no longer necessary, and with increased reliance on external libraries, it's no longer particularly useful. Stacks of printouts are a thing of the past. Line-oriented files are somewhat of a universal standard. Minor quibbles about the interpretation of line feeds aside, pretty much all systems can read and edit ASCII line-oriented text. But beyond that, there's not much agreement on how files are structured. There have been many attempts to make a universal format for structured data, beginning with the ASCII standard itself. ASCII contains 4 control characters, FS, GS, RS, and US, which stand for file separator, group separator, record separator, and unit separator. These provide 4 levels of record structure. But because they've been difficult to enter in a regular text editor, and because no text editor was really written to use them, they've been largely ignored ever since. The most widespread structured data format is comma-separated values, or CSV. This format is not particularly well standardized, and it's extremely limited in what it can express. But its compatibility with text-oriented tools makes it a natural bridge between the structured and the unstructured. More recently, complex structured formats like XML and JSON have attempted to build a better bridge. They're editable in a text editor, but still parsable by the computer. But these formats are caught between being a good binary standard and a good text standard. They are at once defined by their standards as recursively parsable structured data and by convention as line-oriented text. Programming languages have a similar problem. C is nominally whitespace agnostic. You can write a C program all on one very long line if you're not afraid of your coworkers. C is parsed according to a well-defined context-free grammar, so there's no need to worry about lines. Except for the minor issue of C preprocessor directives, which are line-oriented, and the use of line numbers in compiler error messages. Writing either of these languages means keeping the compiler's grammar and the human reader's expectations in sync. Some languages have a pretty well-defined right way to lay out code in text and a tool to enforce this. Python's black and Go format, for example. You can edit your code and then pass it through the appropriate tool to make sure your formatting agrees exactly with the rest of your team. But you still have to understand both worlds. The programming language Lisp is famously homoiconic, meaning same representation. Lisp programs manipulate data structures called S expressions. Lisp programs are themselves S expressions, so it's natural for Lisp programs to manipulate other Lisp programs. On the other hand, the C standard library only has really good support for line-oriented reads, and that's what ends up baked into most other programming languages, including Python. So, if you're writing a program that reads files, it's easier to write it in a line-oriented way, even if it is a program for manipulating source code. This is why the C preprocessor and revision control systems are all line-oriented. It's the easiest way to do it. But most syntax is not line-oriented. In fact, in many languages you can write perfectly valid programs all on one very long line. So why are we still writing in text files? In short, we write line-oriented code because the code we already wrote is good at reading and writing line-oriented files. Our languages aren't homoiconic, but if we're careful with how we format our code, we can pretend they are. Python doesn't execute your Python source directly. Instead, it first parses it into an intermediate format, the abstract syntax tree, or AST. This is a convenient way to arrange the code in memory before compiling it to Python bytecode. Katie Bell talked in more detail about the AST earlier today, but just to summarize, the AST is a tree of nodes, each of which represents some part of the program, an if statement or a block of statements, part of an expression or a single identifier, for example. They're arranged in a tree, representing the non-linear structure of your program. You can peek under the hood of the AST compilation process using the AST module. When we compile code, the compiler has to parse it into an AST. While we're editing the code, most editors do some kind of parsing just for syntax highlighting. Then they write it out to disk as line-oriented text, and the compiler has to parse it again, if it can. Writing code which doesn't compile is kind of useless, So why not just edit the AST directly? An editor which worked directly on AST nodes would never allow you to write syntactically incorrect code, by definition. Syntax highlighting would become trivial. You could display the code in whatever way suits you. Fonts, line lengths, indentation sizes are all just a style sheet over the AST. And it's easy to convert the AST to Python source or a tree-like format such as JSON. The development environment could also compile directly to Python bytecode and could even keep track of changes and update bytecode in place on running code. I'm a huge fan of rapid development cycles. Waiting to see updates is a distraction and a drag. Imagine a development environment smart enough to keep track of the bytecodes you changed and rerun only the tests which executed those bytecodes. A structured editor has the potential to do all this and more. Text editors were a useful way to bootstrap a Unix development environment. The same editor could be used to write code, or edit data, or write a memo. It's the Unix worse is better philosophy. Simplicity wins out over correctness, consistency, and completeness. With structured editing, we could provide an interface to the programmer that allowed them to concentrate on programming, not manipulating text. By reducing languages to a simple grammar of nested syntax entities, plus styling to apply a typical presentation for that language, we can have a single structured editor cover many languages. We could even use our structured editor for writing text documents. After all, HTML and LaTeX are structured languages too. Okay, so it'd be relatively easy to replace the text editor with something AST-oriented. A bigger issue for the adoption of non-line-oriented files is revision control. To allow multiple programmers to work on the same file concurrently, revision control systems must merge changes. First, a common ancestor is identified, and then the changes made by each programmer are extracted. Each file is compared to its ancestor line by line, looking for parts which have been added, removed, or modified. Then the two sets of changes are combined. Combining changes is one of those things which sounds easy, but is remarkably difficult with an algorithm for. The standard diff and merge tools are line-oriented. They coordinate the addition and removal of lines of text. They have no understanding of the deeper syntax or semantics of the file, and only really work on text files with many line breaks. Reformatting or shuffling parts around leads to very large change sets, which rarely merge without conflicts. A conflict arises when multiple changes occur to the same section of the code, and the merge tool cannot determine which outcome should take precedence. Generally, these conflicts are marked to warn the programmer that they will have to take manual action to resolve them. This also means that the output of a merge of two valid programs is not necessarily a valid parsable program. This is problematic for our structured editor, which has no idea how to handle a syntactically invalid program. However, a merge utility which does understand the syntax tree of the programming language can avoid these issues. Whatever the language, JSON or XML, C or Python, we can exploit the structure of the syntax tree to compare and merge syntax tree nodes instead of lines. Instead of just looking for the insertion, deletion, and modification of lines, our change operations become about subtrees. Common subtrees can be identified, and list-like structures such as blocks can be merged. Changes where a subtree is moved can be identified and treated as a move rather than a delete and insert. This would be a godsend for anyone who's ever felt guilty for making a large, conflicting change by altering the indentation of a whole block. There are some difficulties. For a start, the Python AST doesn't encode comments, which some people may feel are kind of important. They'd have to be added into the tree somehow. The merge tool would have to work out how to represent conflicts while fulfilling its promise to always admit valid code. When two developers make overlapping changes, a conflict occurs. It needs a human to resolve it. In conventional merges, it's marked with some special lines. The merge program doesn't even bother to make these look like program code. After all, the program syntax is almost certainly broken anyway. A structured merge has to emit parsable code, so conflict markers have to be inserted as a syntax tree node, such as a comment, and other parts of the tree may have to be patched up to maintain the correct structure. The exact rules for how to merge tree structures are not easy to define. How far can a subtree move before we treat it as a new subtree? If one programmer changes the contents of a subtree and another programmer duplicates that subtree, should the changes be inserted twice? But as the saying goes, we do these things not because they are easy, but because we thought they were going to be easy. If we try to merge these change sets with a conventional merge, we might end up with a conflict like this. But with a structural merge, which understands what a block actually is, we might end up with this. Which, while it probably doesn't do what you want, is at least valid parsable Python, and you can edit it in your structured editor. I've talked about history a lot to try and explain where a lot of the assumptions we make about code come from, but not every historical system is founded on those same assumptions. Back in the 60s, Ted Nelson coined the term hypertext as follows: a body of written or pictorial material interconnected in such a complex way that it could not be conveniently presented or represented on paper. Modern computer systems are definitely interconnected and complex and cannot be conveniently represented on paper. So presenting them as a printable, linear, 80-column document is a little strange. To come at this from another perspective, here's a rectangle representing the 800 by 500 pixel resolution of the VT220 80-column display. Here's a somewhat larger rectangle representing a modern 4K monitor. We have a lot more room to move these days. We can even consider using graphics. Freed from worrying about our programs as text, we can present them and work with them in a way which is more interesting. The education sector has begun to explore the world of visual programming. Scratch and a number of Scratch-like imitators move the main input mechanism of programming from typing to drag and drop. Other environments such as LabVIEW and CodeRed allow programming by dragging connections between nodes, modeling the flow of signals and data. These are data flow languages, where the order of code execution is completely unrelated to the way components are arranged on the page. It therefore makes a lot of sense that their presentation is mobile, two-dimensional, and non-linear. Spreadsheets are another example of a data flow language. Formulae aren't evaluated based on their position on the sheet, but rather by their position within a directed acyclic graph of cells. While spreadsheets may not be a programmer's idea of a programming language, they are one of the most accessible and widespread forms of programming. These sorts of languages have been held back by a lack of tooling. It's hard to get work done effectively in a language without the ability to merge and track changes efficiently. But the same is true of more conventional languages. In JavaScript, for example, function definitions are hoisted to the top of their enclosing scope. So for example, you can define co-recursive functions like this. These two functions are not really defined in any particular order. It's irrelevant which comes first. They could be swapped without consequence. The same is true, much of the time, for Python classes and methods. They refer to each other, but the order of their declaration is unimportant. JavaScript is also famous for its callback hell of functions which pass pointers to other functions. This is a close match to the underlying event model, which reflects the reality of network programming, but it can make reading the code rather bewildering. One solution to this is to use promises to hide the essential callback structure of the code. Another solution might be to work out a more readable way to represent this essential structure. Don't change the event model, change the view. Inspired by these examples, I developed Flobot, a visual data flow-based language for controlling robotic toys. Sensors and actuators are represented by nodes at the top and the bottom of the screen. Their shapes indicate their purpose. Sensors only have outputs and actuators only have inputs. There are also functions which have both inputs and outputs. The robot's behavior can be adjusted by dragging connections between sensors, functions, and actuators. Changes to connections are reflected in immediate changes to the robot's behavior. Invalid connections, like connecting analog to digital or an output to another output, are simply not permitted. I found that this was a great advantage in that there are no wrong Flobot programs, only surprising ones. The Flobot programs are compiled to Python, which is then executed by MicroPython embedded on the robot. Flobot is effectively a visual editor for a subset of Python. With a little more work, code can be flipped between the visual data flow representation and the native Python representation. Not all Python syntax makes sense in the visual metaphor of Flobot, so those parts could be rendered as a black box function. But the general shape of the code, the flow of events from sensors to actuators, would exist in both representations. This idea of code having multiple representations simultaneously is particularly interesting. Different representations might prove more effective for different people or for different tasks. Perhaps it will prove useful just to change your own perspective from time to time, just to unstick your thinking. This goes beyond just code. If a function is a structured piece of information within a project, then so is an issue or a requirement. We track changes to code very closely. Why not track changes to issues the same way? We have editors capable of cross-referencing functions to their callers and callees. Perhaps we could do the same with requirements and issues and tie every line of code to the issue which it fixes. Programs are complicated and structured and deserve better than to be treated as text files. Perhaps that's true of our documentation as well. Now we're thinking of code as trees of nodes and documents as trees of nodes. Perhaps it's time to abandon the idea of files altogether. A project would be one giant tree, perhaps an append-only structure or a CRDT, into which we would pack all the discussion, requirements, issues, code, and so on, cross-referenced and change-controlled. Our systems are often spread across multiple platforms and multiple languages, often across multiple continents. Code isn't just code. There's requirements, issues, discussions, tests, APIs, and logs, all scattered across disparate, incompatible systems. To solve a problem, we have to jump between issues and line numbers, log messages and version IDs. Imagine for a moment navigating through all those resources seamlessly, connecting and correcting as you go, all spread across the several million pixels in front of you. It sounds like science fiction. What are we waiting for?